Hello all. Sorry I can't be there today. Came down with a bug pretty hardcore. So rather than share it all with you, I figured maybe we could do this the flipped way. And so what I've got here for us today is a little video walking us through the practice quiz, presenting some information for you guys, and then you can get to doing some practice work and get started on your homework. All right, so what I'd like you guys to do is in your notes, practice quiz A, you will see that you have this information provided for you. Please do me a favor, hit pause on the video and have everybody enter this information into your calculator. Please be careful. You have to identify which you think is the explanatory variable first, then the response variable, because that's going to be your list 1 and list 2. So go ahead and do that. All right, so hopefully by now you've got all this data entered in and we're just going to go through the process. So the first thing that you're supposed to do is to make a scatter plot and to describe the association between the size of the diamond and the cost. So personally, I hope you picked size of the diamond as being your explanatory variable and the cost as your response variable. So let's see if I can get this to work. Now, when I was looking at my calculator, I went ahead, turned that sucker on, typed all my information into my lists. My plots have been turned on to scatter plot mode. So now I'm just going to do zoom, stat, there's my data. Now, if I were to describe that, I would say there's a definite positive association. So that would mean as the size of the diamond increased, the cost in US dollars also increased. Remember, if you do a scatter plot in your calculator, you have to draw this and you have to label this axis down here. This is my explanatory variable, so size of diamond in carat, and this axis over here is the cost of the cost in US dollars. Oops, wrong way. So strong positive linear association, cost increases with size. Very simple. We have strength, direction, form, and there are no unusual features here. So it next says create a model to predict the diamond costs. So we're going to go back to our calculators and we're going to do stat, calc, and again remember we don't want the first lin reg, we want the lin reg that is the stats form, so that guy right there. Again, we have X list, Y list, frequency list is plain, nothing, and you have to do your store reg equation in order for the rest of this to work. If you don't do that, you're not going to be able to do your residual plot, which I'm going to show you how to do. So boom, there's all my information. So remember, A here is my intercept, so -558.52. B is my slope, 8225.04. R and R squared. So R gives me both directionality and strength. R squared is the percent of the variability of Y accounted for by the change in X. So the model that you should put together here is this guy. Now they are missing a couple of things. What they're doing here first is they're saying this is the general equation that they came up with. That's not really what we're using. What we're going to be using is this guy down here, because we're trying to make the predicted cost. This is just setting you up, showing you which order your variables are going in. Don't worry too much about this stuff here. This is what a computer output would get you. What you need to see is it's got the constant. The constant is your intercept. That's that guy. That's your intercept, sorry. Sick brain, not working too well. And carat, you look here, that's your explanatory variable, that's your slope. Now, these guys right here aren't going to be too important. We're not going to worry about the standard error coefficient, T, P. You'll notice it's T because we're actually using a t-test here. We'll talk about that more later. But what you need is this. This is the standard deviation of your errors. This is your R squared, and ignore the R squared adjusted. We don't deal with that. Then it says, do you think the linear model is appropriate? Well, in order for the linear model to be appropriate, you have to check your assumptions and conditions. So we're going to have to look at our residual plot. This is what we really want a residual plot to look like. Our data was categorical, it was straight enough, there were no real outliers, so we can do a residual plot. And if you look, this residual plot shows nothing, which is exactly what we want. All you have to do for this guy, when you're labeling it, is call it resid. That's all you need. You don't need units on that at all. Now, how do you get the residual plot? Hopefully all of you guys are going back to your calculators with me. I need my calculator to pull up. Oops. Okay, here we go. So what you're going to do is you're going to go back to Stat, into your Edit List. And under List 3, you're going to go up on top of it. You're going to go to Stat, Edit. For List 3, arrow up and then do second stat for list. And because we did a store reg equation, you should have this option of doing a resid. So I'm going to hit enter, enter. And this is going to give me the residuals. This is actually right now here calculating the difference between the predicted value, which is in my Y1, and my observed value, which is in list 2. So now I'm going to go back to my calculator, go back to my stat plot, but this time I don't want to graph list 1 against list 2. I want to graph list 1 against the residual. So again, I'm going to go to second list, grab that resid. This is what you want it to look like. So now I'm going to hit enter, zoom, stat, and there's my residual list. And you can see hopefully here that that matches pretty darn well. So those steps again, we went under stat, edit. In list 3, we didn't have anything. So you arrow up to the list 3, you hit second, stat, and then down at the bottom, you should see resid. If you don't see resid, that means you didn't store your reg equation. So you're going to go to resid, hit enter, and it'll calculate all of your residuals. Then go back to stat plot and plot it your x against your residuals instead of your x against your y. And then we just zoomed stat. And there's your graph. Again, if you get this pulled up in your calculator, you have to put it on your paper. Now, we had already calculated our residual line, and it says interpret the slope of your residual model in context. Your model is always going to have the same interpretation. You take your slope, and then you're going to say the model predicts, or all sorts of different ways to say that, each additional carat will increase the cost of the diamond by $8,225.10 on average. Okay, you've got to have that word on average. Remember, this is a prediction. This isn't what we know is going to happen. Heck, it's not. There are other things involved. The intercept of the model, this was a little bit weirder. That was negative 508. I'm sorry, guys. Sickness, not working. Negative 558.52. That means if you have no carats, that's how much it costs. Now, why is that unrealistic? Yeah, I'm not going to pay you to not have a diamond. And these are always things that you want to do. If you have an intercept that doesn't quite make sense, you always want to talk about it, because there are some models that only work within a certain range of data. Go ahead, take a second for me, and I want you guys to work out these last few problems. So please push pause and then come back when you're done. All right, the correlation, that was your R. Now, we didn't need to take the square root, but make sure that if you do, you always have to take the square root of the decimal. I was really pleased with you guys doing that in class the other day. And it was positive. And we know it's positive, not just by looking at the value on the page or in your calculator, but because the graph actually went uphill. So this is our correlation. Now, R squared, which is that portion inside there, that is the percent of variability in diamond prices that can be accounted for by the size of the diamond. So the percent of the variation in diamond prices, so that's my Y, that can be accounted for by the variation or change in the size of diamond, that's my X. Now the last one's asking me, would it be better for a customer buying a diamond to have a negative residual or a positive residual? Well, you like it if you pay less than you thought you'd have to. And since your residual is observed minus expected, my observed we want to be less than the expected, so that means that number is going to be negative. All right, so getting into chapter 8, really it's just looking at the nuts and bolts of things that can happen with regression. Little quick summary here. You can have a lot of different reasons why data does not work, which is why we always have to include our graphs of the residuals, our graphs of the data. Everything has to be shown and checked. And that's because we have our straight enough condition. The data itself has to be straight. This is assuming you have quantitative data to begin with. You want to be careful and look out in your regression model to see if you have any groups. We saw this the other day when we were talking about cars with horsepower and fuel economy. When you've got different groups, it often behaves differently. So we always want to take a look at that and make sure that our straight enough condition works, which we can re-examine in our residuals. Because just because it looks like it works for one part doesn't mean it's going to work for the whole thing. And the residuals really tell us the whole story. Anything we might have missed by looking at the original data plot should show up in the residuals and help get us started in the right direction. Now, you have to check both plots. You have to graph both plots, and both plots have different requirements. In your original data plot, you cannot have unusual points. That means no strange outliers, nothing that's going to be pulling your data one way or the other, because one little point will tell you more about your regression analysis than anything else, because it can have a really strong pull on it. Points with high leverage are points that are far from both the X average and the Y average, X bar and Y bar. Remember, we said those are the only points that we can guarantee is on a regression line. Well, the further away you are from average, especially if that point is away from the group of the other points that we have, the more influential those points can be. They can alter the regression model. It can even make a negative association appear positive, no association appear strong, strong association appear weak. So it's always good to remove whatever that outlier is and perform the regression analysis again. Because sometimes it tells us, all right, maybe there was a mistake in the data, maybe the data was correct. We have to be prepared for both ways. So if you do see an outlier, do it twice. That means you're going to have to show the second residual plot without that data point. Now, we have to be careful because your unusual points, and this is the reason why we do it, we don't know if these points were mistakes, we don't know if there's a change in trend, or if there's just not a very strong predictable model. So don't just remove your points and move on with your life to make things prettier. If you're going to remove the points, tell us why, and again, make sure you show all of your calculations both ways. Now, extrapolating. Extrapolating is like one of our deadly sins of statistics. Extrapolating means that you're using the range of data that we were given, of all of our observed data, and we're going beyond what our domain was. So from the smallest observed X to the greatest observed X, we don't want to go without that outside that window. We don't know what happens when time changes. Extrapolating is basically making predictions into the future. And again, we don't know if our model is going to hold in the future. This is what we believe held true in the past. Extrapolation from the mean, and that means basically going further and further and further from the mean, can lead to really silly and useless predictions. So basically what we do is we look at where the average is, we look at the set of the range, and we don't want to go too far outside of that range. You don't want to go more than, like, let's say 10% outside of the domain. So this is just a really cute idea about extrapolation. It says, Mr. Fox, about your homework. I assigned questions 1 through 20, yet you only did questions 1, 5, 10, 15, and 20. So I figured you could plot my results, find the best fitting curve, and extrapolate how I'll do on the others. Yeah, he's stupid. but still, it was pretty cool. Don't do that. Please don't do that. You will be punished. Okay, lurking variables and causation. Now, this is why it's important to not just report the R squared or the R value. You actually have to look at the data because there could be other things at play. No matter how strong the R squared value is, how straight the line, we cannot say that A causes B. Typically, these data points are all observations. They're not done through experiments. So we cannot show a cause and effect. There's always a possibility that there's a lurking variable driving both of the ones that we've observed. And there's no way to kind of filter that out. Now, observational data is not an experiment. So that's why, again, we go back to the idea of a lurking variable. Lurking variable is a variable that you're not accounting for. Maybe you know about it, maybe you don't, but it could be affecting both X and Y points. Maybe not equally, but it might be affecting both of them. So here's a really great example. This is the average life expectancy for a country related to the number of doctors per person. And what's really cool here is you see they did a re-expression, which we're going to talk about in Chapter 9. If I look at this, there's a pretty strong linear association, positive, and it makes sense to me that your life expectancy should go up if there are more doctors per person. But here's life expectancy versus TVs. You know what's weird? That's an even stronger association. That data is a lot less spread out. Still life expectancy, but now this axis is the root of TVs per person. That's just been re-expressed to make the data more linear. Why would TVs be a better predictor of life expectancy? Well, TVs are cheaper than doctors. You can send TVs to poor countries and boom, life expectancy goes up, right? No, not at all. But if you want to think about the actual living standards of the people in those countries, higher living standards usually going to equate to more TVs. You can afford to buy more TVs. If you can afford to buy more TVs, you can probably afford to buy better food, make sure that you stay healthy. Yes, go to those doctors. But just the TVs themselves aren't going to increase your life expectancy. That's not really what has to do with it. So individuals versus means. If we look at all of what we've got here, there's a strong positive linear association between weight and height, which makes sense. If you're going to be a taller person, typically you're going to weigh a little bit more. It's not always exact. If you look here, we can have very heavy people at any height, and I've known quite a few very, very skinny tall guys. Now, what we've got here is we have gone from individuals to, we're taking all of the groups here, each of these row of data points, we're finding the average. Obviously, we have less points. Averages kind of eliminate the appearance of outliers, so it looks like an even stronger association. Don't do this. This is not a good idea. The reason why is if you're working with summary values, which would be like our plot of the means, is it shows less variability than we saw on the initial graph. Now, once you're talking about means, you're cutting back a lot of those extremes. You're pulling all of your data points to the center. And because of that, you're not seeing the variability. That's also going to cause you some issues because means vary less than individual values. But remember, the actual spread of the data is very important to us. They're not going to show us as much scatter in a set of means than we would see of the original data. That means we can lose how strong of a fit our line is. And once you've gone to means, you can't go backwards. There's no recovering from that. So the trick here is, whenever you're doing a scatter plot, that scatter plot must be of individuals, not of averages. Because averages are not going to show outliers. Averages might hide the pre-existence of groups. Averages might make a line look like a much better fit than it is. Do not look at averages, look at individuals. Once you've gone to averages, you can't go back. All right. Now this states that we're going to have a quest next class. We're going to see how well that works out. I'm going to post the full notes here, including worked out solutions on SLMS. You guys are welcome to look at that during class. And this is your homework. Now, I cannot stress enough to you guys, do this homework right now. Use your books for help. Okay, I think you can definitely handle this on your own, but give it a shot. All right, I'll see you guys next time.